Hi, Clive.
Hi, Franz.
Hi, Chris.
Good evening, Chris.
Evening.
Hi, Seth.
Hi there.
Hi.
You want me to display something, don't you, Sev?
Yes, but
Uh,
wait, do the
yeah,
uh,
I just want
read
to
first.
let's get it, find it. Where is it? So yeah, so everybody doesn't have to wait for that. I think this is the updated one.
Yeah, second page.
Okay. That one there.
There we go.
Okay. Radio.
Good.
Yeah. So, um, so well, hey, Anton.
Live.
Yeah, you threatened to join us this evening.
I did. I gave you 24-hour notice.
Long enough to prepare.
Uh-huh. Warning,
Yeah,
Anton.
yeah. How are you keeping?
I've been doing good, man.
Good,
How about
good.
yourself?
Well, our our flat, as we call it here, like apartment, is in complete chaos. We're moving on Thursday,
Ah,
and but I've kept my computer plugged in, and I'm surrounded by boxes and bags.
Thanks for hosting nonetheless.
What was that? I beg your pardon?
I said thanks for hosting
Oh
nonetheless.
yeah, yeah. This. The show must go on, Greg. That's how I say it to myself. Yeah. We have a new person, Robert Fry. I don't recognize your name. Welcome to the meeting. Are you there, Robert? Robert Fry. I think Robert Fry. Maybe Robert Fry. It's just a name. We'd love to, but we like people to, I always ask newcomers, people we haven't seen before, to introduce themselves very, very briefly. If you're there, Robert, I'd love to see you and hear from you. But maybe Robert isn't connected. Well, it's time we started. Um, Time to start. So, who would like to? Is there any, who would like to suggest something for the agenda? I know you've got something, Sev.
Yeah. I am Aerostat, and what I'm looking for is feedback from the group, uh, critical, constructive
Yeah,
thoughts.
right. So, what do you call it? ISA, aerostat,
AMR,
AMR.
atmospheric
Yeah, let's write it in there. Atmospheric methane,
atmospheric methane removal aerostats.
aerostat, aerostats. Yeah, comments. Yeah, comments like that. Yep. Okay. Seems a rather small crowd this evening. We usually get, I bet it tends to fill up. Uh, Good morning, Brian.
Morning.
Welcome to our show. Because this is a public one, this one, I believe. Yeah. Um, so any other suggestions here?
Clive, I would like to speak about our dry scrubbing system.
Right. So dry scrubbing system. So this is a shipping
Well,
system, ship
shipping
scrubber,
flue gas
ship. So should I call it dry
scrubbing.
scrubber like that?
Yeah.
Okay. All right. Uh, Good
It's
afternoon.
in
Yep.
principle, it works similar like Seth's.
Similar like Sev's.
It's
Uh, what
it has
is
only another base.
right. Okay. All right. So let's hear about that then. Uh, Okay. Anything else? Any sort of update from you, Anton?
Nah,
Nothing
not
exciting.
yet.
Yeah,
Soon though.
great. Yeah. I wonder about talking about chemistry, but it wouldn't really be anything that hasn't been discussed before uh, about HCl. Well, that's not much. Um, I'm not unhappy about that. I'll be happy if we finish early today. But these meetings tend to, as we know, take on a life of their own. So let's begin with you, Sev, please. Yeah,
Right. Can we bring up the slide then?
yeah.
Now, folk here will know we've got a number of systems trying to address the atmospheric methane problem. We have Oswald's, we have earlier work by Clive and Franz, we have Franz's original work on iron salt aerosols, we have the ship scrubber, we have ferrocene, we have the things which the Chinese are doing to burn things to make it rain. And basically, we need to investigate all of these and see which ones have got the best potential and, more importantly, can be deployed quickly, safely, with a scale-gated increments, so that you can start small, find out any problems, fix them, and go on to the next scale. I was first helping Oswald out with his aeroplane method of
Yeah, let's see. I
putting
got
up.
my video off.
Oh, hello, Robert. Yeah,
Hello,
hello.
there I am.
Do you want to go
Okay.
back to Robert now,
Yeah, yes,
Clive?
yes. Thank you, Sev. Yeah,
Bye.
Robert. Welcome to this meeting.
Hello. I was
Hi.
having a little technical difficulty, but I finally got past it.
Yeah, well done. Do you mind? Would you give us a very brief introduction? Very, very brief. Tell us, your background, please, because we haven't seen you
Oh,
before, so that's the only reason.
you,
Yep.
you have actually, you're just
Have
not
we?
remembering.
Oh, sorry, I don't
Yeah.
remember. Just
Oh,
remind us
well,
very briefly.
Been a little while.
Yeah.
I was on when Seb Clark gave his talk in recently. I'm Robert Fry from Omaha, Nebraska. I was ran a laser ablation manufacturing group for a little while, and was with CTAC Technologies for a while in Omaha, and with Transgenomic in Omaha. And before that, I was a associate professor of chemistry at Kansas State University, and that's enough.
Okay. All right, then fine. Thank you very much. That's great.
Hmm.
Okay. That's I don't quite remember, but okay. I'm not sure. Right. Sev, please.
Right. Well, Robert's expertise in chemistry may be of great use to us here. So
Okay.
our problem was, how do we get ferric chloride up into the atmosphere enough so that it can scrub the atmosphere of pollutants such as, in particular, methane, but
Right.
also of black carbon, of volatile organic compounds, of black carbon, PFAS, and other nasties, ozone. Others have talked about using planes or balloons or things like that. There was the SPICE program proposed in the UK a while back, headed by Hugh Hunt, which was wanting to pump, in this case, sulfur dioxide, I think, up into the air from using a tethered balloon. That ran into problems of community acceptance. What I want to do is to propose to the group that there's a very low technology way and of putting together several well-proven technologies to do this at small scale, but also going up to global scale. And the diagram you see in front of you is a very rough picture of how this might work. Basically, it can work on land or sea, and because it's dealing with ferric chloride, which is used a lot in wastewater treatment, but is also a bit of it is highly acidic and a little bit nasty, so you don't really want it around large areas of population. So the best place to have it is out in the middle of a big ocean or on an island or something like that.
Yeah.
And the best way to get material up high enough into the atmosphere, which is a few hundred meters at least above the surface, where the winds are stronger and where the turbulent mixing occurs, particularly during daytime, is to pump it up in small amounts and then spray this stuff out. Now, one of the problems with ferric chloride is that you want it to be in nanoparticulate size, i.e. very, very small, so that it's just large enough to intercept the UV rays, which can do its photocatalytic transformation of methane, but not large enough so that it sinks out of the atmosphere. So you want something probably between 20 and 50 nanometers in diameter, and that's really hard to get. You can get it by dissolving it in water and spraying it out very finely. That's one way of doing it. Another way is to simply sublime it, to heat it up to its sublimation temperature of 315 degrees Celsius or so, and let it evaporate out, a bit like dry ice evaporates out, and then the gas condenses a little bit to form nanoparticulates. That's quite difficult to do, but not impossible. But a really good way of doing it, I figured out, is to actually mix a powdered form of the ferric chloride with a bio-oil, a low-grade bio-oil, which you can get from plant mass or old seaweed or almost anything or organic. And provided you can desiccate it to take away the water so it doesn't turn the ferric chloride into acid, you can then pump the slurry up and spray it out of the back of what I'm suggesting is a boomerang-shaped aerostat, which is a bit like the old blimps, but in aerodynamic shape. And once it's pumped out in a hollow cone spray, you can have a little electrically driven igniter just where the spray comes out to basically flare it. And flaring it will heat it up very quickly, will vaporize the powder and get you just the right plume of ferric chloride nanoparticles. And the prevailing winds in many of the oceans are westerlies, and if you put these units powered by floating wind turbines in those areas, you can then have that plume travel probably about halfway around the world before it gets it attracts too much water vapor and is rained out. And over that time, that plume is each of the nanoparticulates is transforming several hundred methane molecules per minute into carbon dioxide and water. So a single particle can, we haven't quite, experiments will need to work out just how much methane it can destroy, and this is methane at 2 parts per million in the atmosphere. So it's very diffuse, but of
Yes.
course the atoms in the atmosphere are moving around very, very quickly. So in a given second, a single molecule of ferric chloride will probably be impacted by several thousand molecules of methane, some of which will react with an ultraviolet rays and the ferric chloride to oxidize.
Is that a catalytic mechanism?
It's a photocatalytic mechanism.
So I think
Yeah,
one small bit
Franz,
yeah.
Franz is the expert in that,
Yeah,
and maybe he can tell us a bit more about it. But basically, the photon hits I think normally either a molecule of hydrochloric acid or else a bit of ferric oxide, because it oxidizes up there.
Yeah.
And there are several reactions which turn it into chloride radicals. And chloride radicals are something like 16 times better at oxidizing methane than they are even hydroxyl radicals, which are the ones which normally clean our skies.
Right. That's right.
So could people come back to me then, having read some of the text underneath, come back with criticisms, questions, or suggestions on this idea, please?
I've got a bunch of things I could say, but let's see. Would anyone else? If no one else jumps in.
But
Okay,
just
Franz.
a point of clarification, Seth. Is the aerostat buoyant in its own right, or is it relying on winds to keep it elevated?
It's basically a blimp. So
Right.
it's filled with helium, and the helium is what keeps it up. But yes, the aerodynamic qualities, if the wind is reasonably strong, would also help it up, and would also help. It's got a long umbilical cord with tethering it, and also through which the ferric chloride solution is pumped up using electric micropumps.
So it's just the buoyancy has to obviously be greater than the weight of the umbilical cord to keep it buoyant.
Yes.
So that's a calculation. Yeah. Okay.
Yes.
Yeah. Very interesting. Yeah.
They have managed tethered aerostats up to over 2,500 meters high. So 500 to 2,000 we know is eminently practical, and that was using a tethering cord. I suspect it was probably of carbon fiber, but it might have been of steel. I don't know.
Okay,
I
so
only want to
yeah.
give a short explanation. This iron 3 chloride is a photosensitive, and if it is hit by a photon, it goes to iron 2 chloride and plus 1 chlorine atom. And this chlorine atom starts oxidizing methane. It makes a methane radical and goes back to HCl, and the methane radical then oxidizes with oxygen and other things, it lasts to CO2 and H2O. And if you can do the evaporation of iron 3 chloride by a flame. Use a simple flame and a solution of iron 3 chloride in an organic, and combust it, and then you get HCl and iron ferric oxide, and the ferric oxide is also in nanometric dimensions, and HCl is a gas, and they recombine later on after cooling again to ferric chloride. That's all.
So it's completely circular and
Yes.
self-replicating, if you like.
Yes.
It'll keep on happening endlessly until the ferric chloride is removed, probably 2 to 4 weeks later by rain. The turbulence in the troposphere is enough to take the flume from, or probably a portion of the flume, maybe half, above cloud making levels, and therefore that will last longer than ferric chloride below cloud forming levels, which is probably rained out in a few to several days.
Yep.
And the beauty of this is if you're using an artificial intelligence system and communications to manage the system remotely, you can then say, okay, well, we don't want to spray it out when rain's about to happen because we'll lose the effect of it too quickly. So we'll stop it for then, and when it's beautiful sunny conditions, we'll start it again. And you can also vary the rate at which the material is pumped up. My guess is the material might be 4 parts oil and 1 part ferric chloride by volume, and you can probably pump it up at rates between as low as 10 kilograms per hour and as much as 1,000 kilograms per hour, and going to many sprays on each of the aerostats. So if the aerostats are in a line 10 wide on one side of a floating wind turbine and 10 on the other, you can have a 20 kilometre wide band of this iron chloride plumes being mixed both laterally and vertically, so that by the end of a week it's covering half of that latitude band around the world. And you can choose which bands you want to use. You wouldn't use it in the doldrums because there isn't enough mixing air there. You probably wouldn't want to go too much over the heavily populated land areas of mid-latitude Europe and Asia, but you'd want to do a lot of it in the big expansive oceans, both the Southern Ocean, Pacific, Southern Atlantic, and indeed the central northern Atlantic, where you're far away from people, so that by the time it gets to where people are, it's well and truly diluted, mixed, and basically is completely harmless to people.
Okay,
in the North Atlantic, you have also a natural iron 3 chloride from the Sahara dust, and in the tropospheric air over oceans, you always have ppbs of HCl. So a little bit of iron 3 chloride you will have also from nature, also over Atlantic.
Thank you, Franz.
So you wouldn't have to do so much of it over the Atlantic, which is good.
Yeah. Thank you. Yeah, Greg, please.
Yeah, thanks for describing this. You generally described the action of it and how fast it would operate and et cetera, but you said you hadn't yet done extremely detailed calculations of how efficient it would be, but just generally, just to get an idea, order of magnitude relative to the scale of the problem, how much of a dent would this system, with each of these or some collection of them, have?
My surmise is that a ton of ferric chloride would probably reduce hundreds or thousands or millions of tons of methane.
And what's the global methane in the atmosphere?
It's 2 parts per billion, two parts per million, and you'd want to take it down to probably as low as you can go. You know, you'd want to get it down to at least a quarter of what it is. I think
So-
it's
yeah.
doubled in the past several decades.
So how many of these would just roughly how many of these particular each of these setups would
I guess you'd need to have a few thousand wind turbines if you wanted to do the whole world.
Mhm.
Yeah.
Okay. I just wanted to get some sense of scaling. Yeah, thanks.
Yeah, I mean, Franz's paper from 2017, was it 200,000 tons of iron trichloride a year? Was it, Franz? To half the
We
methane?
thought 300,000.
300,000 was it? I can't remember the
Yeah.
number. So 300,000 tons of ferric chloride, is that?
Yeah.
To halve atmospheric methane. Something like that? To cut it in half?
Okay.
I'm not sure.
Can't remember. Yeah.
Which
Yeah.
numbers
Yeah. I mean, the thing is that to get it to there's a law of diminishing returns. You know, once there's only 3 molecules of methane left in the air, you need
I
a
got it.
huge amount of ferric chloride, to cover the whole air. So to take it to an extreme example, yeah. Chris, please.
I just got a comment about the picture you've got for a deep sea mooring of thing. I don't know how deep you were thinking of, but I think when
Any
you
depth.
mentioned it previously, I think you talked of deep sea, i.e. thousands of meters potentially.
Yes.
And deep sea moorings are something I know a little bit about. It is a very specialist and quite difficult business putting deep sea moorings in. Oceanographic people do this a lot of the time for various reasons. You need a substantial vessel, and they don't always. Sometimes they go away. You can't retrieve them. They fail for whatever reason. So it's not a cheap or simple process to actually install a deep sea mooring, even for something like the Aerostat you're talking about, because you still need a reasonably substantial thing that's got to withstand the actions of the ocean, irrespective of the blimp that's suspended from it above. So I just think that is certainly doable, but it is probably not a very cheap option at all, I would suggest.
Yes. That the main thing is that it is being done and it has been done, and if you were going to do lots more of it, it probably would become somewhat cheaper than it is at the moment. But yes, you're absolutely right. To do deep sea mooring is difficult, so you'd probably want to start off doing shallow sea mooring, either near islands or in shallow seas, and then move on to the more difficult ones.
I think it's probably unlikely that you would make large savings by just going to larger scale use of such things, because of what you need to do. You need a large vessel. That's going to be a fixed cost. The actual materials you need for the mooring, you might save a little bit on at scale, but I'm not thinking it'd be very large. So I think for deep sea anyway, I suspect you wouldn't even if you wanted to have thousands of these. I rather doubt that the cost of putting them in could come down very much, maybe 10-20% at the most, I would have guessed off the top of my head.
Right. Like you'd look at the diminishing returns. You'd start doing it in the shallow seas and the lands which were not very populated, like Central Australia or the Sahara, and you would then find out what benefit you were getting from that, and you could then work out, well, I can afford to do this depth in this ocean, and there come a point where you say, okay, we've cut down the atmospheric level by half now. We can do a little bit more, but diminishing returns say not much more. Yeah.
Yeah.
Just
Okay.
just one other point. I had a query about your igniting the stuff when it comes out at the back of the aerostat. Is there any danger there of your actual flames actually harming your aerostat? I mean, I presume there are ways and means perhaps to make sure that it's reasonably sort of fireproof at that point, hopefully.
Well, the sprays would be going downwind from the aerostat. So your sensors on the system would tell if the winds were particularly turbulent and going every which way, you might say, okay, this is not a good time to do it. But where the wind was steady, then the burning, the flare would be all taken away from the aerostat, and you might well have the actual spray nozzle several meters behind the aerostat, so there was less chance of it.
Okay.
Okay. Robert, please.
Yes, let me say something about the cost here. I think we need to look at the benefit to cost ratio, because if you really do have a way of taking methane and oxidizing it to carbon dioxide, which is 84 times less greenhouse warming potential per molecule. I should think that you'd be surprised how much people would be willing to contribute to that. If it was going to be $50 trillion a year, that's not on. But the world gross domestic product is only about 110 trillion euros or dollars, and but yet you look at projections of what the gross domestic product is likely to be between now and 2050, and it looks like it may double between now and 2050. Okay, so suddenly what was unthinkable at 50 trillion is still unthinkable at 220, but you're not talking $50 trillion a year. You're talking about a considerably smaller amount. And if you're down at, say 1% of the 2050 GDP at, say, 220 or $30 trillion a year, I think it's going to be viable. When you think about what you're talking about here, you're talking removing the excess methane, which, by the way, I think the pre-industrial value was zero point 0.7 ppm of methane, and so you don't have to eliminate it. You just knock it down. You cut it down by half, and you're down to one. Just cut it down by a little more than half. And then imagine the gross domestic product of the world increasing by double in a fairly short period of time, and I would think it would be a bargain if people had to pay, say, 1% of the gross domestic product on your thing, and if you take 1% of 110 trillion or even 220 trillion, I think you will probably have enough money to do what you're planning right now.
Yeah, I think we're talking of amounts less than 100 billion per year.
To me, I mean, I don't mean to minimize that. I'm no rich guy by any stretch of the imagination. But when you look at what the gross domestic product is going to do in the next 15 or 20 years, I think that people, if you can show them the real benefit here, look, if you take out as little as 1.3 parts in a million, you will have reduced the global warming factor by about what, 20%?
Possibly closer to 30%, but yes.
Closer to 30%. Well,
methane is meant
that's a
to have
bargain. That's
Yeah.
a bargain.
Yeah.
And I think by the way, I think what you're talking about makes a lot of sense as far as the way that you want to do it. I haven't really thought this through much, but what what you tell me sounds pretty good.
Thank you.
Yeah, yeah, good stuff. Brian, please. Brian, are you there, Brian?
Yes, I'm.
Yeah.
Yeah. I think I want to point out an opportunity for cost optimization, and that is there's an opportunity to actually get rid of the deep water mooring and utilize that kite a little more effectively as a sailboat and effectively achieve navigational goals and dynamic station keeping without the expense of the deep water mooring and without, and with perhaps increased functionality as well. And the way it works is you need a hydrofoil underwater as well as the aerofoil above water. And just as a sailboat works with a hydrofoil and an airfoil, you do the same thing with the kite. So there's, this is done manually today when you have kite foilers that are sailing back and forth quite effectively. But in the future, it can be automated as well. In fact, I think Ron Swenson built the biggest kite for a sailboat, something like 4,000 square feet or larger. So it was a pretty large one, and it was very effective and was used in a sailing race boat, at least for trials. And I mention it because you already have the kite. You've got the expense of a deep water mooring, but you can eliminate that expense with the suitable use of a hydrofoil and appropriate autopilot capability.
You just kind of tack back and forth then, do you, Brian? You just tack back and forth.
You can tack back and forth. You can have, backup plans for doldrums and the like. But, this would actually, as the late, great Stephen Salter noted, you can have a single vessel covering a lot more area when it's actually moving. And he was proposing that with his hydrofoiling sailboats that would spray submicron sea spray across the oceans. And they were very light and, quite an elegant design, I would say. So maybe
Nice
something
idea.
similar could be done here.
Yep.
Thanks, Brian.
Happy to contribute that. Thank you.
John McDonald.
Just a few other thoughts, Seb. Rather than the ground-based anchoring system or wind turbine base, perhaps you could have a wind turbine integrated with the aerostat, so that we're actually generating in very strong elevated winds, and they could do the pump power on the actual device. Another thought, you could have tethered winch arrangement like they have on experimental kite generators, so you could generate some energy from the tethering as well, and similar to what Brian's saying, you could have a drogue or a sea anchor at the base. If you're in the Antarctic circumpolar current that circulates around the bottom of the globe, perhaps you could actually have them continuously circulating, although having a hydrofoil would be probably more controllable in terms of navigation. But just a few other thoughts there worth considering, perhaps.
I like it.
Mm-hmm. Yeah. So what you're saying is this is one of the things trying to calculate. You said each atom. Did you say each atom of iron would cause 200 molecules of methane per minute to be oxidized? Is that what you're saying?
Franz and Peter Fikowski are better experts than me on this, but
Yeah.
that's my surmise. Yes.
Yeah. Okay. It's difficult to know with people have started doing experiments. The crew at Copenhagen University, they're the ones that measured air in the Caribbean. I think it was somewhere else as well, but mainly the Caribbean, to calculate the methane removal from Saharan dust. It's quite difficult to do, of course, but they did, and they measured methane removal from iron from Saharan dust. And as Franz says, the air is naturally acidic from, for example, dimethyl sulfide makes sulfur dioxide, so which makes sulfuric acid. So we have acidic air quite naturally, and that near the coastlines or anywhere you have salt in the air, sodium chloride reacts with the acid to produce HCl. So it all produces ferric chloride in the end. And HCl, so HCl it also has a catalytic reaction with methane. Because it boosts OH radicals. And we should keep in mind that most methane is removed naturally by OH radicals. The air is full of the air generates OH radicals all the time from sunlight. And OH radicals attack methane. Methane is this is how Professor Matthew Johnson describes methane. It's rather inert gas, even though we use it to heat our homes and everything and our stoves. That's partly what makes it safe. You know, it takes a bit of a spark to get it going, and then of course you get a chain reaction. It gets hot, and so it keeps burning. But in the air, it's so diffuse; it's very hard. You know, each methane molecule plays hard to get. So you do need a radical, you know, like an OH radical, which is looking to react, you know, with something. It's very, very reactive. But chlorine atoms are also very reactive. They normally go around in pairs. It's Cl2 gas, chlorine gas. But when it's a chlorine atom, it's even more reactive than an OH radical. It's double the weight, and it attacks methane molecules and then produces HCl. So once again, that can react with an OH radical. That does react with an OH radical, releases chlorine again. So the whole thing, having more HCl in the air, actually, also where you have OH radicals, it speeds up methane removal. And the other thing to point out is that it produces this whole reaction. It's not just a simple reaction. There's always a kind of cascade of other reactions that produce ozone, ground level ozone, which is not so great. We want lots of ozone in the stratosphere, but there's additional ozone. We've seen it's quite you can look on Wikipedia. It's rather seasonal, but tropospheric ozone is almost as strong a greenhouse gas that as methane. Methane gets, you know, it's very welcome that there's a lot of additional focus on methane now as well as CO2. But tropospheric ozone is not far behind, you know, ground level ozone is not far behind methane. And there's a lot of it produced where there's pollution, as you mentioned, VOC, but volatile organic compounds. So this is unburned hydrocarbons, all kinds of things, and nasty stuff as well that comes from exhausts. And this is where urban smog comes from. So I could go on and on and on about it. You can read all about it. But as you're saying, Sev, some kind of some kind of reacting to some kind of strong ferric chlorides. And this was Franz's paper. It's saying mimicking nature, because Saharan dust contains iron, so you're actually just mimicking nature by releasing ferric chloride. So my question for me is, yes, okay, it sounds interesting. But you'd have to do a cost analysis. Would it be cheaper than drones? What would be the management cost? You know, to keep it all going?
There's no. Once you've got the aerostat up, there's no running cost. There's only maintenance cost and your pumping and your materials. You could probably do quite a good test for how effective the nanoparticulate was if you simply used a greenhouse. You spray the stuff out in a greenhouse. You have the roof of the greenhouse. You have one which allows in ultraviolet rays, and you simply measure how fast the methane content of that in that greenhouse declined.
Yeah, great. That was my suggestion to you in the last few days. Yes. I'm glad you have taken that, recognized that. Okay. Thank you very much, Sev. Anything else from anyone else?
I could ask if Brian's idea of making the thing mobile, could that be tied into weather forecasting and following rain patterns to steer around them?
Well, potentially, yes, but a lot of the satellite work and the Argo float systems already can provide a lot of that information. There's a few things. No, I think the Argo floats give you ocean temperature profiles, and the satellite data will get you a lot of the info. So I think, it could help in a complementary way, but the primary function would be distribution of submicron sea spray or particular aerosol particles. And, Stephen had a great idea, and that is use these vessels that can move quickly, that can, tack, or they can dynamically station position, use the energy of the ocean, wind, etc. And ultimately, this is a great way to affordably distribute particles on an ocean basin scale.
So if you could just use that to steer clear of rain, you could keep that ferric chloride going more and wouldn't get rained out as often.
The troposphere is going to be a one week time scale. I think you're right. You can choose where to go, but you're going to have fronts coming through every week. And so I think you just count on the ferric chloride lasting a week. That's true for the submicron sea spray as well.
Okay.
And that's the nature of tropospheric aerosols, but that's actually a good thing in that it limits the time scale and the geographic extent of the impact. And that means we can develop local and regional solutions transparently, sponsored by municipalities that care, that want to help lead the way. And this represents, I think, an action front for us to really look at progressing in the coming years with, by putting out requests for proposals to communities that want to help lead the way on climate repair.
Yeah, good point. Thank you, Brian. Okay, anything else? Anyone else? Yeah, it also strikes me. Did anyone see there was an email from John Nissen? John Nissen's with us. That there's more OH radicals in the high intense sunshine, areas of the world, so the tropics basically. And so methane, I hadn't seen that before, so thank you for that, John Nissen. Less methane in the tropics because it gets destroyed that much quicker. And so methane is going to be warming the kind of, subtropics, the temperate zones more, and possibly even, the polar zones that much more when they're sunny. Yeah. Okay. Yeah, John, you got that. Okay. What else do we have on our agenda? We have 2 items today. Oh yes, Franz, your flue gas dry scrubber.
Yes, in 2020, the IMO decided that ship fuel shall reduce in sulfur content to 0.5. Until then, 3.5% had been allowed. But in 2021, they announced another rule that ships can use this 3.5, which is much cheaper, 3.5 sulfur oil as fuel when they use scrubbers to clean them. Most ships then big ships worked with scrubbing systems, and they used mainly wet scrubber. And meanwhile, it is well known that despite rules of cleaning the scrubbing solution before it is let into the ocean, that the ocean surface is severely polluted by this wet scrubbing system. So there exists also on the market a dry scrubbing system. They clean the flue gas by a temperature at round about 400 degrees with NH3, that's ammonia, to reduce NOx to N2. And then they go with this pre-cleaned flue gas into a section of the stack where it is neutralized by sodium hydrogen sulfate, not sulfate, carbonate. That's the same like baking powder. It's mechanical crushed baking powder
and that
mixed
neutralizes
with the flue gas, and is the flue gas is then rather neutralized, because SO2 reacts with this, and H2O and oxygen is also there.
So you get sodium sulfate particles out of it.
And you make salt particles, sulfate particles, sodium sulfate particles. Yes. And these must be, they are not given into the ocean. They are put on board because it is polluted with hydrocarbons, polycyclic aromatic hydrocarbons, which are not the best for health. And then the gas, the flue gas, is let out, but this must be stored on board. So it's a rather expensive process, but the oil, the high sulfur oil, is much cheaper than the 0.5% sulfur oil, around about $100 per ton. That's the reason why such systems are used.
Yeah.
Because the 0.5, they have no necessity to do anything according to IMO until now.
Yeah, International Maritime Organization.
So
yeah,
we thought we can make this process much cheaper, and we came. We found out that over the ocean exists ammonium sulfate. This ammonium sulfate is, you find it not only over urban areas or near shore areas, but also on the Southern Ocean, where it comes effective. The ammonia comes from the ocean, is emitted by the ocean, by the phodic zone, and dimethyl sulfide is emitted from the phytoplankton litter, and they combine. They both go as gases into the atmosphere, react and oxidize, and dimethyl sulfide produces sulfuric acid, and reacts with ammonia in the air and makes very small particles of ammonium sulfate. And these ammonium sulfate particles act as cloud condensation nuclei. And we see meanwhile, that the phytoplankton, the photic zone layer, is suffering from all kind of, the fish content in ocean, the whale content in ocean, all goes down, has gone down. If you look to the pre-industrial situation, there were much more multiple of animals existing in the photic zone than today, including krill. So these produced a lot of how do you call it, urea and feces and so on. And the ammonia content in the atmosphere was much higher. And also the phytoplankton content by this natural fertilizing from had been also much more in the ocean. So also dimethyl sulfide was much more in the air because the ocean emitted.
Yeah. So there's
meanwhile,
more. Yeah.
Meanwhile, not only did the animals go down, also the phytoplankton goes down because of acidification of the ocean and stratification, because the phytoplankton has problems to get a fertilizer from below. So we came to the conclusion clouds had been much more in the pre-industrial time and much denser or whiter or brighter, because their droplets had been much smaller than today, because ammonium sulfate particles in the air are extremely small. They are in the nanometer range. So we thought, how could we recreate this situation and bring back the cloud production, because clouds are very necessary for the planet and for the climate, because they produce a lot of reflection of white clouds. If you look to today's ocean clouds, they are very transparent. They have bigger droplets and lesser droplets than these bright clouds on the continents, which were much more small particles than over the ocean. So we had the idea to produce the situation like pre-industrial by use of SO2 from the flue gas. And we want to do the same like the nature did, and ammonia is much cheaper as a neutralizing agent than sodium bicarbonate. So we have a price less than 1/10 of sodium bicarbonate for ammonia. So we think we use this system of a gas reaction with SO2, and in the flue gas reaction, which is cleaned before from these polycyclic hydrocarbons and soot and so on. And we use only the cleaned flue gas given an oxidation catalyst iron 3 chloride, about 1/10 or so, or 1/5 of the SO2 amount. And then let them react in the gas phase and give a dilution to get not too concentrated gas reaction with ammonia, because we want the primary particles, not the coagulated particles, because they become too big. And then let it out of the ship stack, emit into the troposphere, and the warm aerosol will come by to cloud height, and where it is wet enough, it makes bright clouds. And the interesting thing in these very tiny droplet bright clouds is that the surface of these smallest particles, smallest droplets, has a positive charge, and the interior of these particles has a negative charge. From OH, you have a surface.
So the small cloud droplets make more OH radicals, don't they? Because of this edge effect.
Yes, at first this effect produces H2O2.
Yeah, hydrogen peroxide.
Hydrogen peroxide.
Yeah.
And this is known since the last 2-3 years in the Zarre lab. They found this, and also
in Lyon.
In Lyon, in the Lyon lab from
Zare is Berkeley, is he? But Berkeley, California, is he?
He is
Stanford.
Stanford.
Yeah.
Stanford.
Yeah.
So this condensation reaction produces much hot H2O2. So our iron catalyst we used for oxidation as oxidation catalyst for SO2 oxidation reacts in the cloud with H2O2 and produce a burst of OH radicals.
That's another well-known thing, that a little bit of iron.
That is a normal Fenton reaction. Fenton reacts.
Yeah.
And the hydrogen chloride reacts with the OH radicals and produces chlorine atoms, like we had before with Jeff's idea. And this so we have a big cloud, and this is a reactor. Cloud acts as a reactor, and all methane and all tropospheric ozone, which is in this cloud, disappears at once.
So many things go together. So it's the iron.
But I think it has a chance to get realized, because it is a much cheaper scrubbing system, like existing scrubbing systems, and they can use the cheap oil. And if they use ammonia, it's much cheaper than these other solid alkaline things.
Sodium bicarbonate. Yeah, it's a great proposal.
And above these bright clouds, you have the chance, you have the reflecting light. And in the reflecting light, you have much more UV photons.
Yeah.
And everywhere where UV photons are, there you have more OH radicals.
Yeah.
That's another thing. So we know in the pre-industrial time, we had a much better situation of methane depletion. And so by this, we could arrange a good reflection of the planet, methane depletion, so many things, and it is cheaper than the existing system.
Yeah.
That's it.
Yes, thank you very much, Franz. Yeah. And that's right. A lot, at least along shipping lanes, brighter clouds where the ships go. And it all goes in the right direction, as far as we can tell.
Yes.
The iron helps
And
the
we
process in the ship.
can arrange it in a way that when we go near the shore, we will have no emission of these sulfate particles.
Yeah.
But when we are in the open ocean, we can switch the system and make clouds.
Yeah. Thanks, Franz. Thank you very much. Robert?
Yes, Franz, did I hear you say that the sulfate, ammonium sulfate particles would be small enough to make finer droplet clouds?
Yes,
Okay.
because you know the effect if you have a bottle of HCl and a bottle of ammonia water, and you put them together, you see the white smoke.
Yeah.
And
that's ammonium chloride, isn't it?
Yeah.
Yes.
This is a very small ammonium chloride particles.
Yeah.
Right. Now, does that depend on the available humidity? I assume it would, but you have
Yes, to make clouds, you are. It depends on the weather.
Right.
If you have dry air, you can't make clouds. But
right.
Even the haze you produce has also a small albedo increase, and you have always the iron 3 chloride system with which is working by photosynthesis. Not by the Fenton system, but by the photosynthesis.
Okay. Now, what my real question is going to be that if you had a way to raise humidity locally, for example, a dimethyl sulfide is one of nature's cloud seeding agents. If there were a source of dimethyl sulfide available in the same location or on board your ship where you're making the ammonium sulfate, would that adding a third element there along with that aerosol, would that make a brighter cloud?
The difference, there is a big difference between normal salts and sulfuric acid small droplets. You know, when you produce from the SO2 gas sulfuric acid, so-called in the statu nascendi, I don't know when. In the first moments when sulfuric acid it comes into existence in the air, it is in the gas phase. It exists. Later on, it condenses to bigger droplets. But sulfuric acid has an extreme strong
hygroscopicity.
Yeah. And this makes much bigger droplets than normal salts, which start also from the very small nanometer So
I mean,
Well,
there's plenty of sulfur dioxide coming from the flue gas, especially you have 3.5%, sulfur fuel. So
and
I don't really understand, Robert, why you're saying an additional dimethyl sulfide source, because there's lots of
well,
sulfur
yeah,
coming
I'm
in the
just saying
fuel.
if it's one of nature's main cloud forming agents and it is volatile, it is a gas.
yes,
Uh,
Yeah.
if you mix that in up higher or and then seeded those clouds with ammonium sulfate.
you know, ammonium sulfate is a much better bright cloud producer than sulfuric acid or a pure dimethyl sulfide, because there is no difference if you use dimethyl sulfide or SO2 as because both produce sulfuric acid at the end.
Okay.
Yeah. Yeah. I think dimethyl
And
sulfide.
the interesting thing is sulfuric acid droplets are bigger than droplets made from ammonium sulfate.
Mhm.
And the problem is what I said before, that the surface of these smallest droplets, because the surface is strongly banded, this makes the smaller the droplet is, the higher is the higher is their positive surface charge.
Right. Yeah.
So if you have big droplets and very small droplets, big droplets has a low surface
Right.
load, and the smallest have. If you have one big droplet and a crowd of smallest droplets, each of the smallest droplets pushes the other small droplets away. And because the big droplets has a weak field of positive, so the small droplets push the neighboring small droplets into the big droplets.
Yeah.
Therefore, these clouds, which have a mix of big and small droplets, will rain out very fast.
Yeah. So there's no point, you're saying there's no point in mixing dimethyl sulfide in there if the sulfuric acid is already, SO2 is already providing the sulfur, is that right?
Yeah, for instance, yes. It is it is not only cheaper, it must be because we have the ocean surface acidification, and
Yes.
the ship traffic produces also acidification.
Yes.
And so we neutralize it. And what comes in the ocean when the clouds rain out, this all comes down in the ocean, this ammonium sulfate. And it would even be, it is no sulfuric acid, it is a salt. And even ammonium sulfate is also, as you know, a fertilizer. That means it has a weak fertilizing activity on the phytoplankton.
Okay, so you convinced me that you convince me I shouldn't bother to mix dimethyl sulfide in with the SO2 of the ship.
But
okay, what if I have if I create a massive source of dimethyl sulfide by itself? Is there sense in mixing ammonia in that? If I could do that over parts of the sea to generate unusual amounts of dimethyl sulfide by itself, so they would be taking the place of the SO2 from the ship.
Yes.
Would the cloud production that you get from just making a great deal of dimethyl sulfide would that be enhanced by mixing ammonia in that cloud? Would that also make smaller particles than just dimethyl sulfide alone?
I think when you have pre-produced cloud droplets, you make them bigger by even if you give more ammonia, or even if you go more sulfuric acid, they become only thicker because they act as cloud condensation.
Right.
Really.
But you have to think about the reaction. What's the reaction between the DMS, dimethyl sulfide, and ammonia? So dimethyl sulfide, if I think Franz told me, I think you told me a long time ago, dimethyl sulfide is not very nice stuff. It's a bit poisonous if it's concentrated. But of course, from phytoplankton, it's not even.
It's a stinky substance. It's a stink. Yeah. Because when you are on the near the shore, you have the typical smell of the ocean in the nose,
right?
And this is a dimethyl sulfate.
It's very reduced, isn't it? So you've got
sulfide,
the two methyls.
Sulfide, not sulfate.
So sulfide, yeah. So it's sulfide. It's very reduced sulfur. So it's got a lot of oxidation to do before it gets to SO2, and then more oxidation and hydration to get to sulfuric acid. And only then is it ready to react with ammonia to make ammonium sulfate, which is then stable. It's a stable and neutral salt. So dimethyl sulfide, I think, that's not. That's the way it works from phytoplankton, but from ships, it's almost ready to go because the SO2 hydrolyzes and oxidizes to make H2SO4 sulfuric acid, which then reacts with ammonia to make ammonium sulfate. So I think Franz's ideas. If you're from a chemical background, Robert, and you know chemical companies that especially people that make ammonia, or people that might want to sponsor this, I think we'd be very interested to talk to you. Yeah. But not. I don't think dimethyl sulfide is much help.
Okay.
Yeah. I don't think so.
It's rather expensive, much more than SO2. You can use SO2 by sulfur burning,
Yeah. Yes. Yeah. Thank you, Robert. Yeah. Keep talking to us, and if you have contacts and things that we might be able to take it further. Thank you very much. Brian, please.
Yes. Well, I'm glad that Robert mentioned dimethyl sulfide, and you touched on how it's produced prolifically by algae. It is actually one of the main products of ulva, which is a prolific seaweed, the fastest growing multicellular organism on our planet. And so there is a copious source of dimethyl sulfide. And while in high concentrations, it might be somewhat adversive, I do think that the ocean spray smell, the ocean air, people seem to love. So at least the metabolic products of dimethyl sulfide are commendable, if not the dimethyl sulfide itself. And as a natural aerosol, it's not that toxic in the ocean. People have been living with it for thousands of years. So I think it's all about the dose makes the toxin, if you will.
Yes.
Yeah.
And from that perspective, let's use those natural examples. And we think of dimethyl sulfide as more of a mariculture approach, and maybe the sea spray as the shipping approach. But maybe they need to go hand in hand in some way. So, when we're growing seaweed, we'll work to measure the dimethyl sulfide. And when we're tracking ships, we'll do the submicron sea spray. But if there's some overlap, I'm interested in hearing about it. Certainly, they're complementary.
Yeah.
Do you agree that that is a recognized cloud seeding agent?
Well, yes, and it's beyond cloud seeding. I would call it a cloud nucleating agent. Los Angeles has had for half a century a cloud seeding program, which is an attempt to get increased rainfall in the Southern California basin, which is commendable. I think in the what the opportunity exists is to bolt onto this government paid program and government subsidized program and provide a precursor, and that is with dimethyl sulfide and some micron sea spray and other aerosols, we can provide more clouds to seed. And I think that is a fundamental opportunity to tie in with a socially accepted and government funded program today. And so the idea that we need more clouds to seed, particularly in a warmer world, is a key opportunity. And dimethyl sulfide figures centrally in the regeneration of the marine cloud layer, brightness, extent, duration, etc.
So what I'm thinking of is a means of making a great deal more than what nature does right now.
Well, look, you're gonna. It's nice to go there. However, let's choose things that are easy to do initially. In other words, we'll get a bunch of controversy on enhancing something. If what we found is if we go to restoring the pre-industrial level of cloud cover, extent, and magnitude, then there's a great deal of social acceptance. In fact, Mark Twain said the coldest winter he ever spent was a summer in San Francisco, likely because he had the benefit of a copious kelp forest and other algae growth in Northern California, which, by the way, has diminished 93% as far as macroalgae in the last 20 years. So the challenge and the opportunity is let's just get back to pre-industrial, get that social acceptance, move forward with practical local and regional projects, and actually recover that brightness and recover the marine clouds that LA is trying to seed.
Okay.
Yeah. Great. Thanks, Brian and Robert. Ron, please. Hi, Ron.
Oh, hi, Clive. Thank you. And thank you very much, Franz. That was quite interesting. And I thank you for sharing that. I'm waiting for your report.
Yes.
Yeah, so whenever you can get that, and also, of course, it would be good because I put the link to the open letter in there that I so all of you know about, but we are promoting methane as a key short-term cooling global method, and all methane elimination and reduction, and also tropospheric aerosols. So, there's a lot of, I think it would be really good to have some of the latest kind of thinking in your report, because it's very hard to follow. Of course, I'm not a chemist, so but
you can use it, but we want to make a paper from it.
Yeah. Okay. Well, why don't you send me and let me know what because we could put it as a reference to our matrix, for example, that we are intending to try to publish the open letter with that link to the reference. If that would be okay, we would say, you could frame it however you want, ongoing research or whatever. And yeah, so that would be excellent. Of course, I encourage, all of you, many of you probably, we need, I think I counted 27 more signatures to make the golden number of 42 to match Siegert, and that's kind of what we're after. And I'm hoping that with something like 250 HPAC members, we could get another 27 signatories, but the first 27 will be the ones that we're going to add to the letter. So I really encourage you, if you are interested, to look at that and see if you would be willing to serve as a co-editor. One other comment just on Robert Fry's some of the economics.
Sorry, Ron, can I just say,
yeah.
I don't think I've signed the open letter. And I haven't seen it. I didn't realize, or I forgot that we're all so busy. We don't realize we're supposed to sign something. We haven't signed it. So I would say send it out. Send it out again. So if you haven't signed this, and maybe give a brief paragraph of what it is, that we're signing. So we know that yes, I need to allocate time. I need to spend 10 minutes looking at this to see if I really need to sign it. So I think that's the only reason people haven't signed it, because people, if they miss it the first time, that's it. They've missed it. So send it out again. Anyway.
Okay. I will. I put a link here, and I will try and do a little paragraph or something. So
Some
people
sort of
know
reminder.
what it's
Yeah.
about.
Yeah.
With just one other short comment to Robert, just so you know, I'm an economist by formal training, heterodox economist, but there is a lot considerable thinking that in spite of the optimistic estimates of doubling GDP and all this stuff, that the GDP will actually may start collapsing by the 2040s due to the climate issues. So I would take some of those optimistic estimates with a grain of salt. I mean, we just don't know. There are really calamitous things that could be are already happening, frankly, impacting GDP, like all the insurance failures and so forth already, in the US I'm familiar with, but the AMOC, et cetera, et cetera. So this is, yeah, just a note. Thank you all.
Hey,
Yeah.
if it's up to us, we'll fix it.
Yeah.
The climate, and that'll make the GDP go.
Absolutely. One
Well,
more person. Yeah, go on,
we
Ron.
need to cut carbon. We need to decarbonize as well really quickly. So, I think, yeah, I'm all for growth, but it's got to be growth with a less of a footprint, and ecological and carbon.
Yeah,
HVAC has
agreed.
had the answers for so long. It needs a tourniquet, it needs cooling. There's ways of doing cooling that's much, much cheaper than, decarbonization is needed, but that's a huge, much bigger heft. That's the high hanging fruit. Why not take the low hanging? It's not ideal. It's not the best, but given they failed to take the high hanging fruit, anyway.
You're preaching the converted here, guys.
Yeah, exactly. Well, this is going to go out publicly, so we hope.
Yeah. But what I want to just emphasize is that the cooling is not a fundamental solution. At some point, we can't just keep cooling.
Yeah, I agree.
We need to get the work on the fundamental stuff really quickly, as fast as possible. So
yeah. Thanks, Ron. Chris, please. Chris Vivian, you have your hand up, Chris. We can't see you. Chris?
Yeah, just to follow up what Ron was saying about the economy, there's a link I've just put in the chat from a group, and it's talked about recalibrating climate risk report. And it basically says, I'll just read a couple of sentence or two of it so you know what we're talking about. It says the report challenges the assumptions of indefinite carbonate growth, revealing that experts identify meaningful probabilities of an economic collapse at warming levels between 3 and 4 degrees. And it argues that damage functions must evolve from smooth linear projections to frameworks that account for non-linear thresholds and capital destruction. So they're basically saying that very much supporting what Ron just said about you can't just take economic progression forever, getting better and better.
Yeah. Yes. And this has long been known. Even 2 degrees is going to be terrible, and 3.
Yeah. But
the
economists seem to be ignoring it.
Yeah.
Most of them anyway, not all of them.
Yeah. Okay, that's it. Any last comments? Because we're nearly to our 90 minutes. I'll say thank you very much for joining me again and joining us all again. And see you again in a couple of weeks. I'll be in a new place. I'll have moved house by then.
Thank you.
Bye-bye.
Have fun.
Bye-bye. Yeah. Bye-bye. Bye all.